All right, so this video is going to be on the E1 mechanism. So hopefully you've seen the E2 mechanism already. It's going to be similar to the Sn1, the E1 is, and then they are going to be competing reactions. And so, first of all, the kinetics. This is just like Sn1, first order, and the rate equation is K times the concentration of the alkyl halide, or Rx, where X can be a good leaving group. And the mechanism is going to be two steps, again, because it's first order. So you form that carbocation intermediate, just like Sn1. And then we've got the four factors that we saw before, where we had the alkyl halide, the base, the leaving group, as well as the solvent. So I'm going to work my way backwards and tell you, of course, that the polar protic solvent is needed, just like the Sn1 reaction, right? And that's because polar protic solvents, they solvate the cations as well as the anions. So it can solvate all of the intermediates. So the leaving group, of course, we want it to be good. So hashtag always good leaving group. Now let's talk about the base. Since we don't want it to kind of have to compete with an E2 reaction, we want it to be a weaker base. And so that's going to be a neutral molecule like water, or ROH, which is just an alcohol. Okay. Now, when we're talking about RX, or the alkyl halide, in this chapter, we have primary compared to a secondary compared to a tertiary is increasing in the rate of the E1 reaction. So tertiary is going to be a lot faster. And we also don't want to forget about the benzylic and allylic halides that are approximately equivalent to like a secondary alkyl halide. In terms of rate of reactivity, that's because of their carbocations are pretty stable because of resonance. So here's our energy diagram for an E1. Looks very similar to an Sn1, right? And that's because it is there are again competing reactions. We're going to have this alkyl halide here, for example. It's a tertiary alkyl halide plus water, and then we end up with a isobutylene. So alkene plus acid, of course, and then our iodide. So once our iodide leaves, we form that carbocation intermediate, and then the water, the nucleophilic or basic water, can attack for Sn1, but for elimination, it's going to remove a beta proton. Okay, so we want to make sure that we're aware of the location of all of our beta protons, and so I'm only going to write this one explicit beta proton and then just kind of circle the other ones to let you know that they're there on those beta carbons. So once we remove that proton, we create that double bond, and then we end up at our final product. Okay, and I've highlighted the pi bond in blue just to show you that came from the beta carbon bound, the electrons between the beta carbon and the beta hydrogen. Okay, sorry. Let's go to the energy diagram. We're going to kind of fill in all the blanks for the reactants and the intermediates, transition state. Now what we want to do is kind of take a closer look at the transition state. So let me make more room for this. All right, so the transition state, remember the first step is the loss of that alkyl, or that iodide, right? And so basically we just have the dotted line for the iodine, the carbon iodine bond, because that's on its way out, and it does end up being negative, so it's got that partial charge. So does the carbon. We have a second transition state, and that is the transition state where you go from the carbocation to the formation of that pi bond. So this formation of the pi bond it's in the process. So we have a dotted line for that, as well as the carbon hydrogen bond, as well as the hydrogen oxygen bond that ultimately forms that H3O plus hydronium ion. And we got to fill in our partial charge, right? Partial charge is, and that's our transition state. So these transition states are really important because as we know, because of the Hammond postulate. Oh, sorry. Let me write this iodine here on the bottom because I missed that in the original setup. So again, these transition states are really important because they help us kind of understand the rates of reactivity. So if we can stabilize the transition state, we kind of affect the rate of the reaction, right? And so it is important to understand these. So where we are partially losing the iodide, right? That's the leaving group. So we have a good leaving group. We're going to decrease the activation energy. And then for the formation of that pi bond in the elimination reaction, it's also important because if we form a more substituted alkene, it's more stable. And the rate of that reaction is going to be faster. Okay, so we should also be able to label all of our activation energies as well as our delta H's, right? So we have 2 of each in this case for the E1 and Sn1 curve. I do want to point out that we also have this higher activation energy on the first step. And remember that higher activation is the RDS, the rate determining step, okay? And this is really where the E1 and Sn1 get their name, right? It's unimolecular because there's one molecule involved in that transition state, or I'm sorry, the rate determining step. Okay, so we're checking off all of the information we've gone over. The base, obviously, we want that weak base. And then the final thing we want to mention is the alkyl halide, right? So when we're talking about E1 and Sn1 and the rates of the reaction, so for alkyl halide, we want essentially the more stable carbocation, just like we wanted for Sn1, right? So it follows the same trend as E2, but also as E1, or I'm sorry, Sn1, right? So if we have, again, we can't have a methyl halide, alkyl halide, right? We have to have a primary, secondary, or tertiary to create that carbon-carbon double bond. And then we're going to increase the rate of the reaction as we go from primary to tertiary. Okay, so remember also that carbocations on a primary carbon are extremely unstable and not likely to form. And so, unless it's, of course, a benzylic or allylic. And so, primary is not going to happen for E1 or Sn1. Okay, and so that kind of helps out when we're trying to eliminate the possible mechanisms for a given reaction. Okay, so again, increase the rate of E1 reaction as we go from primary to secondary to tertiary because of the stability of those carbocations. So remember, when we talk about stability of carbocations, we are talking about the number of R groups. So increasing R groups allows for a more stable carbocation, and so the trend for this one also goes from left to right for a primary carbocation up to a tertiary carbocation. Okay, and when we talk about the additional R groups that are on there, that's helping donate electron density, and we look at this as hyperconjugation. Okay, so remember those adjacent sigma bonds are donating into that empty p orbital of that carbocation. All right, so that E2 reaction is, in theory, a competitor, right? And that's why we want a weak base. We want a weak base so that the E2 mechanism doesn't progress or does not occur. Okay, so they are competitors. E2 needs a strong base in order to move forward, though. So if you have a weak base, it's not going to allow for that E2 mechanism to occur, and we're just going to end up forming the carbocation intermediate and moving on. Okay, so just like the E2 was regioselective, so is E1 because it forms a more substituted alkene, right? And this is, if you don't remember all of the details to that, refer back to the previous videos for that, because there's plenty of detail to talk about when we talk about that. But let's go over an example right here. We have this tertiary alkyl bromide plus water. We can get a variety of, if we have 2 different types of beta hydrogens, then we're going to get at least that, or at least 2 of the different types of products, right? And so we have this di-substituted one, we have this tri-substituted one, as well as this other tri-substituted. However, they are the same product. So despite statistical differences in favoring the two on the right, that is a major product because it's the more substituted alkene. All right, so the question that we're all going to be having is, to start at least, is Sn1 versus E1, right? So how do we know the difference? Well, we have the same conditions, and so honestly, they're useless reactions for the most part, right? Some say a waste of time, others say an incredible waste of time. My boy Conan speaking truth right there. Yeah, so Sn1 and E1, they are honestly competing reactions because you have that carbocation intermediate and a weak base and a weak nucleophile. So those guys are just going to form maybe not 50-50 mixture, maybe 50-50 mixture of the elimination product as well as the substitution product, unfortunately. So in this case, here's our alcohol after the proton transfer. So that's the Sn1 product. And then the elimination product, of course, we're going to have the two different types of alkenes, so the di and tri-substituted. And you're going to get a mixture of all of these when you, like, if you're doing this in the lab. And so that's why these are viewed as generally useless reactions, unless you can kind of take these and move forward to make something that eventually ends up being the same. Other than that, they are going to be pretty useless because we don't want mixtures of products, right? We want to make more of, like, we want to get, I guess, the more bang for our buck. So if atom economy is a thing we talk about in the lab, and you want to make ideally 100% of one thing, and then so E1 and Sn1, no good. Okay, so when is it E1 versus E2? So we did talk about the strength of the base being important. So E2 needs that strong base. Here are some examples that you should be aware of by now. Remember this chicken foot tert-butoxide is the non-nucleophilic strong base. E1 requires weak bases. So it's basically all these, you'll see, or oftentimes what you'll see is all of the above ones, but with the proton on there. So they're the conjugate acids of those bases up there. And again, these are just to name a few examples of strong bases and weak bases. But if you have those strong bases, you're probably going to get the E2. And if you have the weak bases, you're probably going to get the E1. Okay? And also, just remember that the E1 can't occur with the primary alkyl halide. It's too unstable of a carbocation intermediate. And so if it's secondary or tertiary, then you're going to start looking at the strength of that base to differentiate between the two mechanisms. Okay, so let's lay it all down into a little chart. Okay, so we're going to put some factors here, those 4 factors that we always talk about, and then we're going to kind of compare E1 and E2 just in chart form. I know some people like charts, so we're going to do it. If you've got it categorized in your brain, then that's awesome for you. But some people need it kind of organized on a piece of paper. So we've got our alkyl halide, the base, the leaving group, and the solvent. Okay. Here we go. So the rate of the reactivity is going to increase from primary to tertiary with the X through the primary because it doesn't occur. It's the same trend for E2, right? And when we're talking about E2 and bases, we want strong, bulky, non-nucleophilic, ideally. Okay, so DBU and DBN are some new ones that we've introduced. We also have for E1 weak bases like water and alcohols. Okay, leaving group, hashtag duh, right? Good, of course. And then for the solvents, just like the Sn2, we wanted a polar aprotic for E2, and then just like the Sn1, we want a polar protic for the E1. And that's it for elimination reactions, at least E2 and E1 mechanisms, okay? Let me know if you have any questions.